Right. So good morning once again. So today we are going to talk about, we're going to start the next subtopic, that is virtual memory. So far we've been talking about uh, the concepts involved in cache memory and how it interacts with the CPU and the memory, main memory, right? So we discuss a lot of techniques involved in caching. And then finally, we talked about multi-level caches as well, and then had a quick look at some real implementations to get an idea, right? So the thing, how the things that we learned are applied in real implementations. So now we are going to talk about virtual memory, which is which you'll see what it is. Right? So you probably heard about virtual memory when you work with computers. You learn what that is and how that connects to the bigger picture of the memory hierarchy. Right. So to start, let's quickly have a look at how CPU word size and memory address space size correlate with each other. Can someone tell me if your CPU word size is 64-bit, what is the size of memory that is addressable by such a CPU? Right. So word size in a CPU means the size of an operand in that CPU. Right. The size of operand the CPU deals with. So register file will be 64-bit registers containing 64-bit register. ALU will operate on 64-bit operands. Like, right, memory addresses produced by that CPU is again another value, right, coming to the ALU, coming from the register file to 64-bit address. So what is the size of memory that can be addressed by such a CPU? So 64-bit is the word size that we currently have. Right? So if you go to buy a computer, you will find the 64-bit CPU inside it, meaning it will deal with 64-bit operands. Can you tell me what is the size of memory that is addressable by that CPU? What's the number? It's how many bytes can that CPU address individually, how many different individual byte addresses that CPU can come up with. That's the idea, right? So what's that number? 2 to the power 64. Yeah, 2 to the power 64, right? 2 to the power 64 bytes, not bits. Right? So each address the CPU can generate, each 64-bit address will refer to an individual byte in the memory, and the maximum number of bytes the CPU can actually address is 2 to the power 64 different addresses, right? So it adds up to 16 exabyte. That is about 16 million gigabytes, right? So way more memory than the computers that we use have, or even the supercomputers of this day and age have. Way less memory than 16 exabytes. Right? We don't have anywhere near that big memory. But the 64-bit CPU can address that much memory, right? The real memories are very, very small compared to that. So, okay, so it feels like the address range generated by 64-bit CPUs are enough forever, right? If we keep improving the size of memory, we're likely not to hit that 16 exabyte number anytime soon. Right? It feels like that. So if we go one step earlier, right? So 64-bit computing came into mainstream around when? I think about 10 years ago, a little bit more than, right? 64-bit computing. So 32-bit computing was there for a long time before that. Around, I think, somewhere around 2002, 2003, the 64-bit architectures started replacing 32-bit architectures, if I remember correctly. So in 32-bit architectures, what is the maximum size of memory that you can address? It is the address space size. The address space is the range of addresses that can be generated. In other words, the maximum size of the memory that can be addressed in bytes. So 2 to the power 32 is what? What's the number? How many bytes? 4 GB, yeah, exactly. 4 GB, 2 to the power 32 is 4 gigabytes of memory can be addressed by 32-bit CPUs. Okay, so I remember one of the earliest computers that I had around, I think, 2001 or so, 2000, 2001. Was a 32-bit computer. It had a memory of 64 megabytes, right? So 4 GB of RAM seemed like a massive number, nowhere near what real computers had back then, right? So back then was about 20 years ago. So like current 64-bit CPUs, with current 64-bit CPUs, it seems like 16 exabytes is like a massive number which we will never reach. So back in the day, when 32-bit was about to be replaced, personal computers, normal workstations, clients, had around 64 megabytes RAM. It was a decent number back then, right? So 4 gigabytes were kind of memories used in supercomputers, massive supercomputers around that time. So if you go another step back, before 32-bit computing became mainstream, 64-bit was there. Sorry, 16-bit computers or CPUs were there. So 32-bit CPUs started becoming mainstream in early 1980s. So before that, most computers that were being used commonly were 16-bit or 16-bit also. So the maximum amount of memory addressable by 16-bit computers are 64 kilobytes. You go another step back, 8-bit computers like the one that we are building in the lab, you can only address up to 256 bytes, right? Really small number. So these are the address space size. So in other words, the maximum size of memory that can be addressed by the corresponding CPU architecture, 8-bit to 64-bit, right? So the point to note here is that these numbers, the maximum address space sizes, were way more than the commonly used numbers for RAM sizes, memory sizes in the age or era that these architectures were mainstream, right? So these architectures were being commonly used. So what made people replace the architecture were the point that when you start having bigger memories than addressable by the current mainstream word size, CPU word size. Somewhere in the early 2000s to late 1990s, the bigger supercomputers that the world had started reaching this 4 gigabytes memory limit, right? So people needed a way to address more than 4 gigabytes of memory in those computers, even though the personal computers or clients, small computers didn't have that much memory. The high-end supercomputers were reaching that amount of memory, and we needed ways to address more than 4 gigabytes of memory. Therefore, the next bigger word size was introduced into those supercomputer CPUs used in those computers. Then later on, after a while, that architecture became mainstream in normal personal computers as well. So, but at the time the transition is made, the maximum number, 16 exabytes, seemed like we will never reach that number, at least in several generations, right? But as you can see, it has been proven that the number, we keep reaching these limits in a matter of few decades, right? So far in our memory hierarchy design, we assume that the main memory contains one slot for every byte address that our CPU can generate, or the program running on the CPU can generate, right? So that is what we've been assuming so far. CPU produces a byte address or a word address, which refers to the starting byte of that word, right? With the last 2 bits 0 in our examples. So whatever the case, we assume that the memory had the maximum number of slots addressable by the CPU word size, right? So that is like having the entire address space available in the memory for the CPU word size. We assume that. So in our 8-bit CPU that we are designing, we actually have 256 bytes of memory. In the lectures, we discussed MIPS with 32-bit memory addresses or 32-bit word size. What we assume is 4 gigabytes of memory is available, right? It's reasonable since that is usually the case these days, right? So, but as you can see with these numbers, in reality, the actual RAM sizes or memory sizes are very small than the address space size in that particular era of that word size, CPU word size. So currently 64-bit is the mainstream CPU word size, and the amount of RAMs that we are seeing in computers, even in supercomputers, are much, much smaller than the address space size, right? So how is that handled? That is where virtual memory comes into the picture, right? So say in current CPUs, we have 64-bit word size. That means we generate 64-bit memory addresses, but reality is in the memory, there is nowhere near that many slots available, right? Memory has way less slots available. So how do we use all those addresses generated by CPU, all those different addresses generated by CPU? That is where virtual memory comes into the picture. Virtual memory allows our programs running on CPUs to use more memory than that is actually available, right? So 64-bit CPUs can use up to 16 exabytes of memory, subject to certain conditions, even though the real memory is way smaller than that. Real memories maybe in a normal computer, 8 or 16 bits, 8 or 16 gigabytes, right? That is roughly the number that we are seeing these days. So that is a real memory size, but a 64-bit CPU in theory can access 16 exabytes of memory. So virtual memory allows the CPU to do that. How it is done is what we are going to learn. Right? So the core idea about how this can be achieved is by using the main memory as a cache for secondary storage disk, right? So far we've been talking about the concepts of caching for memory, where memory is the bigger entity, memory is the like the universal set. But now we are talking about, we are saying that memory is actually not the universal set, the secondary storage is. Everything is in the secondary storage. Memory is going to act as a cache for the secondary storage. And so that is the core idea behind virtual memory. So other than allowing CPU or programs to use more memory than actually available, virtual memory also allows multiple programs to be run by a CPU at the same time. Right? So when we say multiple programs running on a CPU, you know that a single CPU with a single processor, like we are discussing, cannot run multiple programs at the same time. That CPU will execute one instruction at a time, right? It will complete one instruction at a time. So, but you can switch between different programs, right? Switch between different programs really quickly, which will give the user the impression that all those programs are running at the same time. That is how operating systems use multi-threading to run multiple programs. But in order to support that concept, your memory needs to be shared between all these programs running at the same time, and the operating system needs to make sure that the program is accessing only the memory allocated to that program, not memory allocated to other programs or memory belonging to the operating system itself. So that sharing memory, how to share memory safely and efficiently is also taken care of, also included in the virtual memory mechanisms that we will shortly learn. Right. Okay. So this is the memory hierarchy that we have been looking at so far. CPU is up there generating addresses. CPU thinks the memory is really large and really fast. It doesn't know that there is a hierarchy here. So CPU generates addresses in the entire address space, somewhere in the entire address space that it thinks is that the memory is, right? But it directly accesses the cache, and we discussed about how the cache can optimize the common case to be fast, right? So 99 or even more than that % of accesses can be served at the cache level if you implement the cache very efficiently based on temporal and spatial locality. So only a very small portion of addresses actually go to the main memory. Now we are going to see how main memory is going to be acting as a cache for secondary storage, right? Okay, so this is not as straightforward as having, say, 2 levels of caches. Memory is not like the second level of cache. So we'll have to learn some additional concepts for that. So before we go into the mechanisms, let's have a look at some terms that we use in virtual memory. So CPU, we say, accesses words, right? CPU accesses data words, and the data word may be 1 byte, maybe 4 bytes, maybe 8 bytes. So in 64-bit CPUs, we have 8-byte words. So CPU accesses data as words, and those accesses may be hits or misses in the CPU. So those are terms that we learned when we talked about caching. And we say the cache cache and memory deals with blocks. Cache accesses memory and brings blocks of data, which are about 16 bytes size block, or can go up to 256 bytes blocks normally, right? So these are some usual number ranges. You might have even smaller block sizes or even bigger block sizes on certain implementations. So these terms are some of the terms that we used when we learned about caching. Now, in the memory, we say when the cache is looking for a block in the memory, if that block is present, we say it is a page hit. If that block is not present in the memory, we say it is a page fault. So hit is very similar. We don't use the word miss in the memory. We say it's a page fault. And the main memory trades information with the secondary storage as pages, not blocks, pages. And the page sizes are usually from 1 kilobyte to 64 kilobytes. So these are the usual numbers. So you can see the page sizes are a lot bigger than blocks. So you will have several blocks in a page, in a memory page, right? So when the cache is looking for a particular block of data, the page containing that block may be present in the memory. In that case, we say it's a page hit. Otherwise, if the page containing that block of data is not in the memory, we say we have a page fault and the missing page needs to be fetched from the secondary storage. So that is very similar to the caching concepts that we learned previously, right? So the timing delays or latencies in accessing these different devices, cache, we know that it's one cycle, right? We need to design a cache to be accessed in under one cycle in order to serve the CPU efficiently, right? So a hit can be served in under one cycle. Misses, of course, will need more cycles, but we will have only very few misses. And in the event of a miss, accessing main memory usually contains around 10 to 100 CPU clock cycles. In the event of a page fault, when you have to go to the disk to fetch the missing page, that access costs around 1 million cycles. Right? So that is way bigger than what we have looked at so far. Secondary storages are usually really slow. So you have to spend around 1 million clock cycles to fetch a missing piece of data or missing page, right? So these numbers actually become big factors in certain design decisions that we do. For example, in the event of a miss, we know that the miss penalty is 100 cycles, so the design can be made keeping that in mind. Same with virtual memory. We know that in the event of a page fault, we have to spend that many clock cycles, so the mechanisms make use of that that knowledge, right? So let's see. Right, in this setup, how does the addressing work then? Can we have tag compare in memory? So in cache, we had tag compare, right? Cache can only hold a subset of data from memory. In order for us to know what is the data stored in a particular entry in the cache, there will be multiple memory blocks mapping to the same entry in the cache. So in order for the cache to know which one the stored block is, we needed to store the tag and then perform a comparison. So do we have to do the same thing, implement the same concept in memory? Do we have to store tags and do comparison? It's going to be very inefficient if we try to do it that way. So what we say is the CPU produces a virtual address. What the CPU produces is a virtual address. The CPU produces an address in the total address space, right? The entire big address space that it can access. And the memory is a lot smaller than that. The range of addresses that we have in the memory is a lot smaller. So because of that, we need some way to know if the block that is available in the memory is the one that the CPU actually needs, right? So CPU doesn't have any idea about this memory hierarchy. It just generates an address in the entire address space. If it is 64-bit, it can access any one of the 16 exabyte addresses, right? So memory, on the other hand, is accessed using a physical address. Memory may be something like 4 GB or 8 GB size. So the address that you need to access the memory is a physical address in the range of the actual memory size, right? So the range of addresses that can be available in the memory is very small. Earlier, when we talked about caches, we say the cache can simply send an address and the memory has all the addresses stored in it and you can access it. Now we say the memory can't have all the addresses, it only has a smaller range of addresses, right? So it will be storing a subset of data from the secondary storage. So how is memory accessing now handled? So far we said that memory can be directly accessed. An address is given and that location is directly referred in the memory. There is no need to perform any tag comparison, right? That is what we learned previously when we talked about caching. Now, how can we have this done? Do we need to perform tag comparison? No, that is not going to be very efficient for a memory access that big, right? A memory that big to perform tag comparisons. So that is why what we talked about in set associative caches as well, right? As the associativity grows, the number of parallel comparators you need grows. The number of comparators is increasing with the number of associativity in a cache, and we say it's not feasible to have fully associative caches if the cache is really large. So when we go to the main memory, that condition is still valid. Memory is much bigger than cache, and it's difficult to have a lot of comparators operating in parallel, which is going to add a lot of wire delays, and it's going to slow down the process even more, right? And consume a lot more energy as well. So how do we handle these accesses then? We need a mechanism to translate addresses from the virtual addresses that the CPU generate into physical addresses which you can directly use to access memory, right? So physical addresses have a range of what is available in the memory, the size of memory. If it is 4 GB, 4 billion different addresses, right? So CPU can access anything in its range. If it's a 64-bit CPU, it can access 16 exabytes of memory. So those addresses are called virtual addresses. We need to translate those virtual addresses into physical addresses in order to access memory directly, right? So that is what we are going to look at, how that is implemented. That is the main thing in virtual memory. So let's assume our CPU is a 32-bit CPU. It generates 32-bit addresses, right? That is a 32-bit address. And we divide it in such a way that a part of that address is called page offset. The other part is called the virtual page number. So this is very similar to the offset and the block address used in caching, right? Block address was referring to individual blocks from memory. Offset was referring to individual bytes or words inside that block. So this is very similar. A virtual page number, that portion of the address refers to individual pages from memory. Then the page offset portion refers to individual bytes within that page, right? So in this example, we have 10 bits for the page offset and the remaining 22 bits for the virtual page number. So since this is the 32-bit address, the virtual address space is 4 gigabytes. We can address 4 gigabytes of memory with 32-bit addresses. And with 10 bits page offset, we can address 2 to the power 10 individual bytes. That is, the size of a page is 1 kilobyte, right? Size of a page is 1 kilobyte. There are 2 to the power 10 different bytes inside a given page. And these least significant 10 bits can be used to address those individual bytes. Then the virtual page number has 22 bits. That means this virtual address space contains 2 to the power 22 different pages, each 1 kilobyte size, right? Okay. Then we need to translate this address into a smaller address such that it's a physical address with a smaller number of bits, where a certain more significant number of bits are called the physical page number, and we still have a page offset with the same number of bits as the virtual address, right? We had the virtual address has 10 bits for the page offset, then we should have 10 bits for the page offset in the physical address as well, right? Because the entities are the same, the page size is the same for the memory hierarchy. So then what size memory are we looking at? We have 2 to the power 28, it should be, right? This is that's a small mistake there. Correct it. So 2 to the power 28. So we have 28-bit physical address which can access 256 megabytes of physical memory, right? So the size of the memory is 256 megabytes. Size of our main memory is 256 megabytes. We need a 28-bit address to access that memory, right? Individual bytes in that memory, we need a 28-bit address. And out of that 28 bits, the least significant 10 bits are the page offset. The remaining 18 bits are called the physical page number. It's also called the frame number. Sometimes we call this the frame number. So we say the memory contains 2 to the power 18 frames. as well. Sorry about that mistake, right? So memory contains 2 to the power 18 frames. So the physical page number is the same as the frame number. So memory contains 2 to the power 18 frames, each of which can hold a page, right? So a frame is like a slot in the cache or an entry in the cache, right? So in the cache we discussed, we have slots and blocks can be placed in those slots. So in the main memory, the similar concept is frames. We have frames and pages can be placed in those frames, right? So main memory size is smaller, the number of bits need to address that main memory is smaller than the virtual address space. That is the real scenario. Any questions on this? Do you need any, is there anything to be clarified? No questions? Can we continue? Okay. Right. I hope you can still see the slides. Right. Okay. So, okay, so that is about address translation. Now, I said that virtual memory supports multiple programs as well. Let's see how that is done also before we proceed. Right? Okay. So now we are looking at 2 different address spaces of 2 different programs. One program here, program number 1, is we are showing in green color. It has a virtual address space of 8 virtual pages, right? The virtual page number is 3-bit size. So the virtual address space contains 8 virtual pages. Each of these slots is it's containing 1 page, right? So we have 8 virtual pages in the address space of program 1, and it's the same for program 2, right? So they are running on the same CPU, so it's same. The word size is same. So the virtual address space of program 2 is this, right? So program 1 thinks it has the entire memory to itself. Program 2 also thinks it has the entire memory to itself, right? So both programs are running at the same time. The CPU switches between these programs, and there are each program thinks the entire memory is available for use by that program. Okay, but in reality, our physical address space contains only 4 frames. The memory contains only 4 frames. We have a 2-bit frame number, right? So it's a very small example. And now you can see the memory contains purple pages as well as green pages from these 2 different programs. And the translation should contain mappings from virtual page numbers to physical page numbers or frame numbers, right? So there are 2 virtual pages being mapped to frames in the memory for the for program 1, and program 2 also has 2 virtual pages being mapped to physical frames in the memory, right? So we say, So the memory is full. Note that the memory is full, and you can see that some virtual pages are not highlighted. Only the 2 virtual pages that are available in the memory or mapped to physical frames in the memory are highlighted. The same with program 2. So these highlighted pages are present in the memory. We say these are active pages, right? So that means the program at this point in execution is currently using data words which are in these pages, in the active pages. Those are the ones that are currently used by the program. Think temporal locality, right? The currently used pages are available in the memory, and they have the corresponding virtual page numbers have mappings to the physical frame numbers. Same with program 2, right? So you can see multiple programs can have their active pages in the memory at the same time. And each program thinks it can access the entire memory, entire virtual address space by itself, while the memory is smaller, still contains all that contains active pages from each program that is currently running. So when the program wants to access, or the CPU wants to access a particular data word. Let's say program 2 is running on the CPU right now, and it needs to access a data word belonging to this, the second frame, which I'm pointing to here, right? So data word in that page, this virtual page. So CPU generates an address in that range, and regardless of caching, if we are going to the memory, that virtual address needs to be translated into a physical address, and that translation has to be done somehow. We haven't looked at how to do that so far. We will look at that later. So somehow we need to do that address translation, and the translation will tell us, okay, this virtual page is in that location in the memory, right? That frame in the memory. So that virtual to physical address translation will give us the address to use, access the memory, and find the missing page or the correct page that we want. So what if the program suddenly wants to access a page or a word in a page which is not currently active, right? So it can be the case. So this might be the first time the program is trying to access a word belonging to that page. So that page is not in the memory right now. It's not available in the memory. There is no mapping, right? So there is no mapping from this virtual page to a frame in the memory. So in that event, we have a page fault. The page is not in the memory. The required word is not in the memory, right? We have a page fault. Then we need to go and access the disk. That is going to cost around a million clock cycle, right? More than that usually. So in such events, these page faults are handled usually in software, not usually, always in software, by the operating system. Why is it handled in software? We are going to have a big penalty, around a million clock cycles. So trying to add more optimized hardware into this, if you are going to spend that million clock cycles anyway, it's not going to make a big difference, right? So adding more hardware, trying to optimize this, trying to do this operation in hardware, it doesn't make sense. It's going to saving a few clock cycles is not going to be effective, right? It doesn't compare well with the penalty. So the page faults are usually handled in software by the operating system, right? When you have a page fault, that is, the page is not available in the memory, then the operating system should take over and access the disk and handle that page fault accordingly. So that is in the event of a page fault. But before a page fault happens, we need this address translation every time we want to access the memory, right? Every time there's a miss in the cache, we need to go to the memory, and in that event, we need an address translation. And that event, we are looking at 10 to 100 cycles. So if we can, if we try to do that address translation in software, that is not going to be effective. We had to transfer the CPU to a different program, that is the operating system, and spend hundreds of clock cycles doing this, which is not effective. Yeah, maybe doubling or maybe making the penalty 10 times more. That is not effective. So the memory accessing needs address translation, and that needs to be handled by the operating system, but with hardware support. We should try to optimize that at least a little bit, because that penalty is comparatively smaller to the disk access penalty, and we can try and save some clock cycles by doing some optimization. Okay, right. So that is how multiple programs are supported. Each program can assume that it has access to the entire address space, whereas in reality, the memory shares whatever little frames available between all these programs, depending on what is currently being used by individual programs. Right. Okay. Now, say I said that virtual memory is basically using main memory as a cache for the secondary storage. So there needs to be some write policy, right? We do writes to the memory, and we need some sort of a write policy. So in caching, we discuss write back and write through policies. Write through policy makes writes to the cache as well as memory. That is what we discussed, right? So the same policy doesn't it doesn't look very good for virtual memory, because writing to the memory and every time writing to the disk as well, it's not going to be effective, right? 1 million clock cycles, that is not going to happen. It's not a very good design decision. So write through for virtual memory is not used. Virtual memory typically uses write back policy, right? So remember, we need to track the dirty status of pages here, right? We need to keep track of which pages are dirty or which frames are dirty in the memory, which frames contain dirty pages rather. And in the event you need to throw out a page from the memory back to the disk, evict a page from the memory, then if that page is dirty, you need to write it back, right? So what we're trying to do here is trying to minimize the number of accesses made to the secondary storage. Disk accesses should be minimized. So that is why write back is the policy used in virtual memory. Then we also would like to minimize page faults, right? Because if we have a page fault, that is when we have to go to the disk. So we want to minimize page faults. So how we use the available amount of memory to place pages from disk, usually go for fully associative. Not usually, actually. It's fully associative policy. These are placement policies used in memory. Remember, that is, we don't use an index, right? There is no mapping policy saying a particular page from the memory has to go to that particular location in memory. That is indirect map or set associative placement types. Here we use fully associative placement. That means a page from disk can go to any frame in the memory, right? So it's like memory is one big set and it contains all the frames available. That set contains all the frames available, and a page from the disk can go to any frame in the memory. Then the problem becomes, how do we find a page in the memory? Remember, in caching, when we introduced associative caches, we needed to do store tags and do tag comparisons. And we are not doing that in virtual memory, so we need a different mechanism. And that mechanism comes with this address translation. And how the address translation is done is what is the answer to this other question. How to find a page in the memory? You access the memory to know whether that is the page that you are looking for. How to know that? That is done through address translation, right? So it's a different mechanism. It's not a mechanism that we have used in caching. Caching, we use hardware comparators to do the search to verify whether this is the block that CPU is actually looking for. Now, main memory address translation is done in a different way. And how that is done is by using something called a page table. So a page table is a data structure which is stored in the memory itself, right? It's a separate section in the memory in the same physical address space which stores the address translations. Page table is a list of address translations, right? So here in this example, we have 16 virtual pages in each virtual address space. The physical memory contains 8 frames, right? So some of the active pages from each program's virtual address space are currently mapped to some physical frames, you can see, right? So we have 2 frames from program 1, 2 pages from program 1 currently active with mappings available, and 2 pages from program 2 currently active in the memory, right? So these arrows, the purple arrows and the green arrows, they represent the address translation, right? Virtual to physical translations. So those translations are stored in page tables. A page table is simply a list of address translations. So page tables are also stored in the memory. So you can see a section in the memory is allocated to page table. Note that we have different page tables for different programs. Why do we need different page tables for different programs? Because the mappings for individual addresses can be different for different programs. For example, if you take program 1, this is page 0, 1, 2, 3, 4, 5, right? This is page number 5. Page number 5 from program 1's virtual address space, it's mapped to this, this frame in the physical memory. Page number 5 from program 2's address space is mapped to a different frame in the memory, right? So these mappings for the same virtual page numbers can be different. The physical page numbers corresponding to virtual page numbers, even though the virtual page number is same, the mapping can be different for different programs, virtual address spaces. So that is why we need program-specific page tables. So this PT1, the green page table, it contains all the mappings of program 1's virtual address space. Mind you, when I say all the mappings, not just active pages, everything, right? So there are 16 virtual page numbers in this address space. Therefore, the page table one here, it should contain 16 entries, one for each page from the virtual address space. And the entry should specify if the page is available in the memory, then the entry should specify the corresponding physical frame number or the physical page number. Right. So how does this work then when the CPU or program running on the CPU wants to access memory? It needs to first go to the memory and access the page table. So here, just assume that your program one now wants to access a word in that page. Then it first needs to get that address, the virtual address, translated into the corresponding physical address. So first, you need to access the page table, the corresponding page table for program one, and find the corresponding entry to this virtual page number in that page table, which can be directly accessed because you have one entry in the page table per virtual page. So you need to access the page table, corresponding entry, and read the stored physical page number in that entry. Then you can get that address translated and access the physical memory to get the required data, right? So every time you want to access the memory, you need to make two memory accesses. One, access the page table to get the address translated, then access the physical memory, actually to read the actual data that you want, right? So when you want to access the memory, you need to do two accesses. Page table access, then data access. Any questions at this point? I'm trying to explain this as slowly as possible because I know that these concepts can be confusing. If you have questions, please ask. Okay, so let's continue. Right. Now the problem is, I was expecting this question to come up. Now the problem is how to find the page table, right? We say that in order to find a piece of data in the memory, we need to first access the page table, which is also in the memory. So how do you find the page table? Right? So we still have the same problem, it seems, right? So we introduced the concept of page table in order to store that translation. So we can find those data in the memory. The page table is a way to find data in the main memory. But how do we find the page table? It's also in the memory. It's again a piece of data in the memory. Remember, we said it's a special section in the memory. So what we do is we place it at a fixed location. We place the page table at a fixed location. It doesn't change once you place it. And that location is known to the CPU and the operating system, or the combination of CPU and operating system. How that is known is we include a register in the CPU called page table base register, or PTBR. Page table base register is a special register in the CPU, and it can store the starting address of the page table, right? So in that case, the starting address, so that is the starting address, right? So addresses go from here to there. So the starting address of the page table can be stored in the page table base register. Then comes the problem. You have multiple page tables for multiple programs running, right? The CPU switches between different programs. So there are different page tables stored in the memory at a given time. So how do we know the location of all those different page tables? The solution to that is, when we say multiple programs are running at the same time, at any given instance, the CPU only executes an instruction from only one program, right? So when that program is active, PTBR should contain the base address of the page table for that program. Whenever the CPU moves to a different program, the page table base register should be updated, right? So that is done or handled by the operating system. The operating system is the entity which transfers between different programs, right? Operating system tells the CPU, okay, run this thread. Okay, stop, now run this other thread, right? So that is handled by the operating system, and when handling that, the operating system should make sure to update the PTBR value as well in the CPU to point to the correct page table belonging to the program that is currently running, right? Okay. Any questions? Right. Okay. Okay, so let's have a look at this page table. I said it's a data structure in the memory, right? It's not a physical, separate physical device. It's a data structure stored in the memory. So let's look at it as a table, just like we looked at caches, right? So we have a number of entries. Each entry corresponds to one virtual page, right? So the main element in each entry is the physical page number. So if that page is present in the memory, this is how the address is translated, right? For that corresponding physical page number, this is the virtual page number. So physical page number can be used to index this list, right, to access the correct entry, and then read the corresponding physical page number. And then we have two other bits here, valid bit and dirty bit. So right, so how is this accessed? What the CPU gives us is byte address. We look at that as virtual page number plus the page offset. We take the page table base register, which will point to the start of this page table. That is the first entry of the page table. Remember, this index is not stored, right? So index, the first entry of the page table is pointed to by PTBR, and we use virtual page number as an offset to PTBR, right? That is PTBR plus virtual page number can be used to access the corresponding entry directly. So PTBR, if PTBR is referring to the memory address, that is the start of this page table, then if virtual page number is 2, that is PTBR value plus 2, right? That is this highlighted entry in this diagram. So if virtual page number is 0, then we will be looking at this very first entry. If virtual page number is 1, we will be looking at the next entry. In this example, virtual page number is 2. So we are looking at this highlighted entry. And the value stored that in this slot here is the physical page number. So we read that. Then we take the page offset from the original address, concatenate them, and then we have the physical address. This is the physical memory address that we want to access in the real memory. So that is assuming this page is already active and a frame in the memory is containing this page, the page that is required by this address. So what are these other bits then? Valid bit, it says, is the page active in memory, right? If valid bit is 1, here it says the page is active in memory. That means this physical page number is valid. This address translation is valid. You can read the physical page number and convert the address. If you have a 1 here, if this slot is 0, that means the address translation is invalid, right? That means we don't have a mapping from this virtual page number currently in the memory. It's not current, that page is not currently in the memory. That is the meaning of the valid bit. Is the page active? Is it in memory? Then the dirty bit, the meaning of that is the page inconsistent with the disk? Has this page received a write? So the page data is now not the same as the data in the memory. So why we need that bit is, if we need to throw this physical page number out, if we know, if we need to make it invalid, if we need to throw this out in order to bring a different page and place in that location and update this update this page table entry, then we need to check the dirty bit of the existing translation, and if it is dirty, we had to write the data, the page from the memory back to the disk before we replace that, right? So that is the idea of the dirty bit. Now let's do a little exercise. Assume we have 4 GB virtual address space. That means the virtual page, virtual address, the size of the virtual address is 32 bits, right? Then assume we have 1 GB of physical memory, 1 GB of physical address space. That means the size of a physical address is, you need to compute the number of bits, right? The third assumption is the size of a page is 1 kilobyte. Then the page offset, the size of the page offset, you also need to compute. First question is, how many entries in a page table? Can you answer that question? How many entries in a page table if the virtual address space is 4 GB, physical address space is 1 GB, and page size is 1 kilobyte? Remember, page table contains an entry for each virtual page from the virtual address space. So can you calculate this? Right, so in order to do that, you need to know how many bits are in the virtual page number. 2 to the power 32 is the size of the address space, right? The entire address space. So that is the number of bytes available in the memory, but the page table contains an entry for each page, not each byte, right? So if the page table contains 2 to the power 32 entries, it will take up the entire memory, assuming each entry is 1 byte size, right? So you need to work out how many virtual pages you have. That is the number of bits you have in the virtual page number. To do that, you also need this page offset. What is the number of bits for each page to refer to each page? Sorry, each byte within the page. So a page is 1 kilobyte size. How many bits do you need for the page offset then? 2 to the power what is 1 kilobyte? That is the number of bits, 2 to the power 10, right? So you need 10 bits for the page offset if your page size is 1 kilobyte, right? If we have 1 kilobyte of data in every page, then page offset should contain 10 bits to refer to those individual bytes, right? So that means what is the size of the virtual page number? How many bits you have for the virtual page number? We have 22 bits for the virtual page number. So that means there are 2 to the power 22 individual pages in the virtual address space. That means the page table should contain 2 to the power 22 different entries, right? Each virtual page should have an entry here, right? Okay. So how many entries in a page table? That is 2 to the power 22, right? 2 to the power 22 is how much? It's I think 4 million, close to 4 million, right? So 4 million pages in the page table, 4 million entries in the page table, right? So the next question is size of a page table. What is the actual size of a page table? A page table is stored in the memory, right? So what is the actual size of a page table? We know a page table has 2 to the power 22 different entries. Now we need the size of each entry to do this, right? So what is the size of a physical page number? How many bits to store the physical page number in a page table entry? We need the size of the physical address thing for that. So our physical address space is 1 gigabyte. That means how many bits in a physical address? Physical address has how many bits? One GB. Physical memory is 1 GB. So a physical address should contain how many bits? 30. Yes, that is correct. 2 to the power 30 is 1 gigabyte. So the physical address contains 30 bits, and out of that, offset is 10 bits. So the physical page number is 20 bits, right? So we need 20 bits to store a physical page number in a page table entry. Then in addition to that, we need valid bit and dirty bit. So what we are looking at here is 22 bits, right? But we know that the memory is word aligned, right? So memory is first byte aligned, each address is referring to a byte, and then it's word aligned. We use word addresses. So using 22 bits per entry, you can't divide it straightforwardly, right? Say how many bytes do you need to store a page table entry? Can you say it's say 2 and 3/4 bytes? It doesn't make sense. So since these entries need to be word aligned, we use 32 bits to store one entry, right? 32 bits, one word to store one page table entry. So the size of the page table, therefore, is 32 bits into 2 to the power 22, right? 32 bits into 2 to the power 22, or in other words, 4 bytes into 2 to the power 22. Can someone calculate that number and tell me the number of bytes? 4 bytes, one entry is 4 bytes. We have 2 to the power 22 such entries. So the size of the page table in bytes is should be around 16 megabytes. It should be 16 megabytes, right? If I'm correct. Yes. Okay. So in our 1 GB physical memory, if the virtual memory is 4 GB, virtual address space is 4 GB, we need each page table to consume 16 megabytes of memory. To store each page table, we need 16 megabytes of memory. Right. Okay. Then, so we noted that we use 32 bits to store a page table entry, but we really need less than that. We needed 20 bits for the physical page number, 1 bit for valid, 1 bit for dirty. So there are remaining bits, 10 bits remaining. So some of those bits are used to store other information like say access permissions, which process can access this, or different access permission, memory protection, protection statuses. So all those things can be stored in those extra bits. So we are not going to discuss about that here, right? Okay. So, right. So let's move to the next slide here. Page faults. Now, we said that page faults are handled by the operating system, right? So let's see what the operating system needs to do in order to handle page fault. So a page fault happens when an entry in the page table is invalid, right? We access the page table to get an address translated, and we don't have a current translation for that address. That is, that page is inactive. It is not in the memory, right? So the page table entry will have the valid bit as 0, right? The entry is invalid. Therefore, yeah, it is a page fault. So we need to handle this page fault. Page faults are handled by the operating system. Let's see what the operating system does to handle this. The first thing we need, what the operating system needs to do is it needs to fetch the page from the disk, right? So operating system needs to access the disk and fetch the missing page. To do that, operating system needs a way to know where a page is in the disk, right? We are not going to discuss how disk is accessed. if you're interested, you can go and do a little search on that. Operating system anyway needs to keep track of where each page is stored in the disk, and some data structure operating system needs to use for this, and fetch that page from the disk, fetch the missing page from the disk. Then the operating system needs to find an unused frame in the physical memory, right? So memory contains frames to hold pages. So the operating system should now find an unused frame in the memory frame which is not containing a page right now, which is not containing an active page right now. So in order to do that, operating system needs to track the utilization of memory frames, which frame is currently used, right? So it can be done through the page table as well. So anyhow, operating system needs to keep track of that and find an unused frame in the physical memory, right? Then if you have an unused frame, the operating system can place the fetched page in that unused frame. But if there is no unused frame, if all frames are used, if the memory is full, if all frames are used, then the operating system needs to find an active page to replace, right? All the pages are active, all the frames in the memory are containing active pages. The operating system needs to evict one of those, throw one of those active pages out. To do that, there should be a replacement policy. Operating system should use a replacement policy like least recently used, or first in, first out, or least frequently used, right? So there are different replacement policies. Since the operating system is handling these in software, you can have different complex replacement policies, and based on that replacement policy, select a page to evict, right? So the idea of the replacement policy is to serve temporal locality, right? Frequently or recently used pages should remain in memory, and less frequently used pages, so less recently used pages, can be thrown out of the memory if you need to make space, right? So that is to select which page to replace. Replacement policy comes into the picture. To do that, operating system needs to keep track of page usage by programs, right? So again, it needs data structures to keep track of how frequently a page is being used or how recently a page is used, depending on the policy, right? So once the page is selected, operating system needs to check whether that page is dirty. If the page is dirty, that means it's inconsistent with the disk. So page needs to be written back to the disk in order to before it can be replaced, right? Otherwise we are going to lose data. So if it is dirty, we need to write back the page, then only you can perform the replacement operation, overwrite that page. So all these things, these can be done in parallel to the data fetch, right? So data fetch from the disk, it takes a long time. So while you fetch the data, while the disk supplies the data, the operating system can decide where to put the fetched data, right? So whether you have an unused frame, if there is no unused frame, what page or what frame to put it, what page to replace, then if that page is dirty. If the page is dirty, the operating system can transfer the page to a buffer, and a hardware buffer, and overwrite the newly fetched page, then send the the dirty page in the buffer to the disk to be written back, right? So these mechanisms can be handled like that to reduce the maximum the latency of a disk access, or rather the miss penalty in a page fault. Right. Okay. So we are not going to go into too much detail about how exactly this is handled, but we will have this overall idea, right? So more details about page handling will be discussed in operating systems course in your third year, TO327. So you will learn about all those other mechanisms, how the replacement policy is implemented, how OS keeps track of page utilization or page usage, frame utilization and page usage rather, right? So all those things you can learn in operating systems course, right? Here we are going to talk about one more thing, which is called the translation leukocyte buffer, TLB in short. So the idea of TLB is to avoid accessing memory for address translation. So we said we need to access the memory twice if we needed to access memory. If we had a cache miss and we needed to go to the memory, we need to do two memory access, one for page table, second for data, right? So TLB is a way to avoid this page table access by acting as a cache for page table, right? Another caching, right? Memory hierarchy. This is the third form of caching now we are talking about. So TLB is a piece of hardware. It's like a cache. It is a cache. It's a cache for the page table. It's a cache for the page table, which is a data structure stored in memory, right? While the regular cache is for the entire memory, TLB is a cache for the page table entries, right? So it looks something like this, very similar to the caches that we have seen so far. Difference is the data that you're storing is a physical page number, right? So this cache or TLB, it works based on the locality of page table entries. That is, recently accessed page table entries should stay in the TLB. Page table entries located close to recently accessed page table entries should stay in the TLB, right? So that is temporal locality and spatial locality. It is available in the page table access patterns as well. So the TLB is based on those locality principles of page table entries. When CPU wants addresses translated, it goes to page table, and based on those access patterns, some entries can be kept in the TLB. So majority of the page table accesses can be actually served by the TLB instead of going to the memory for that. That is the idea, right? So here, the valid bit says is the page table entry value, right? So this valid bit is different from the valid bit in the actual page table. The valid bit in actual page table says, is the page in the memory? Is the page active? The valid bit in the TLB, it says, is the TLB entry valid, right? Note that there may be multiple TLB, multiple page table entries can come and reside in the same TLB entry. So whether this entry is valid, that is mentioned, that is indicated by this valid bit here. Dirty bit is the same as before. Then you need a tag as well, virtual address tag, or it can be actually the physical address tag as well. Depends, but no, actually that's the virtual address tag. Yeah, sorry, that's the virtual address tag. And the address translation, physical page number. So in the event of a cache miss, we need to get the address translated in order to access memory. We look in the TLB, and if there is a valid entry in the TLB with a matching tag, we can do the address translation right here rather than going to the memory. If we don't have a valid TLB entry for the current access, then we have to go to the page table in the memory anyway. Right. Okay. So usual parameters. The size is usually around 16 to 512 page table entries, right? A big range, but depending on the design, between 16 to 512 address translations can be stored in the TLB, right? In the usual TLB. The block size is 1 to 2 address translations, right? So not one piece of data is and a single address translation. A block size is 1 to 2 address translation. We don't have bigger block sizes because of the type of spatial locality here, right? So locality between pages are bigger entities. Locality between pages is somewhat less than locality between blocks. So the block size for the TLB is 1 to 2 address translations in a single block. So if there is this here, we are going to bring two address translation, two adjacent address translations from the page table, two adjacent page table entries into the TLB together, right? Then the placement policy is usually fully associative or set associative. If the page table is smaller, closer to say 16 page table entries or so, we can use fully associative. Otherwise, we use set associative because of the same reasons in caches. Larger caches with fully associative, then the complexity is higher, the hit time becomes, or hit latency becomes larger, power consumptions become higher. So placement policies usually set associative or even fully associative for smaller TLBs. Why we need that is we need to keep the miss rate as low as possible. Miss rate is usually less than 1% in TLBs. So more than 99% TLB accesses should be hits, right? So that is why we go for fully associative or set associative placement rather than direct mapped placement. Then the hit latency is less than 1 cycle, usually a lot less than 1 cycle. Then the miss penalty is 10 to 100 cycles because we need to access the page table in the memory in the event of a miss, right? So it's the memory access latency, 10 to 100 clock cycles, right? Okay. Right, so to wrap up, let's have a look at the big picture, right? How the TLB fits into the overall picture of memory accessing, the memory hierarchy that we have learned so far. This is the memory hierarchy. CPU is at the top. It thinks the memory is large and fast, and it directly accesses the cache. Memory, main memory is behind it. Secondary storage is behind main memory. Right, so a memory access request is generated by the CPU or the program running on the CPU. And we say that the address generated by the CPU is a virtual address. Virtual word address usually because CPU reads words, right? With the certain least significant bit 0 to point to the start of the word, right? So the CPU produces a virtual address, word address, and it directly accesses the cache, right? So CPU accesses the cache with that virtual address, not with the virtual address, right? So the cache is virtually addressed. Then if there can be two outcomes here, we can have a cache hit or a miss for that virtual address. If we have a cache hit, we can send the data directly to the CPU without anything else to be done. If we have a miss, then we need to access the memory. In order for us to access the memory, we need to get the address translated, and to do that, we first go to the TLB. In the event of a cache miss, we access the TLB to get the address translated. Then we can have a hit or a miss in the TLB. The translation page table entry may be in the TLB, may not be in the TLB. If we have a hit in the TLB, if we can get the address translated in the TLB, we can access the main memory to retrieve the missing data, fetch the missing data, and send the missing data to the cache. Then the cache will send it to the CPU, send the corresponding word to the CPU. We send the missing block to the cache, cache will send the missing word to the CPU. Right. So that is if we have a TLB hit. If we have a TLB miss, that is, TLB does not contain the address translation. So we have to access the main memory, the page table in the main memory to get the address translated. When we look at the page table, we may get a page hit or a page fault, right? That is, the page is in the memory or not in the memory. Note that if we had a TLB entry, if we had a TLB hit, the page is always in the memory. If we did not have a TLB entry, if we had a TLB miss, we go to the page table and we might have a page hit or a page fault. In the event of a page hit, we can make a second access to the memory to read the data, right? Read the block and send the block to the cache. The cache sends the correct word to the CPU, and the access is completed. If we had a page fault, then the operating system need to access the disk and fetch the missing data, missing page, right? We fetch the missing page, and we need to find an unused frame in the memory to hold that page. If you have an unused page, that is fine. We update the memory, we update the page table, we update the TLB while sending the correct block to the cache and the word to the CPU. However, if the memory is full, we need to replace an existing page in a frame. Then the replacement policy comes into the picture. We need to find that least recently or least frequently used page in the memory. Write that back to the disk if that page is dirty, or override the page, override that frame directly, right? And then update the TLB and send the data word to the cache and the block to the cache and word to the CPU, right? Okay, so that is one way we can look at this bigger picture. There is a different way that this can happen as well. Before that, actually, here the TLB access can happen in parallel with the cache access. Now here we said we access the cache, and if we have a miss, we access the TLB. Since these are both pieces of hardware which can decide hits in under one cycle, what we can do is we can access the TLB in parallel to the cache. If we have a cache hit, fine, we can disregard the TLB status. Or else, if we have a cache miss, then we need to access the TLB. We have already accessed the TLB in parallel, and we have decided whether we have a hit or miss in TLB. So we can overlap the two types, two latencies for TLB access and cache access, right? So that is if the cache is virtually addressed. If the cache is indexed with virtual addresses, then this TLB access can be overlapped with cache access if the cache is virtually indexed, right? Okay, so the other way we can go about this is the CPU generates a memory access, which is a virtual address. We send that virtual address directly to the TLB. Translate it. If we have a TLB hit, get the address translated, and with the physical address, we access the cache. So the cache is physically addressed and physically indexed, right? Cache is physically indexed with the physical address. So we access the cache's physical address. We may have a hit or miss. If we have a hit, all is good. If we have a miss, we need to go to the memory to fetch the data. And we already have the physical address. We go to the memory and fetch the missing data. So that is in the event of a TLB hit. If we have a TLB miss, we need to get the address translated, access the page table. There may be a page hit or a page fault. If we have a page hit, then we can access the data in the memory with the translated address. If we have a TLB miss note, we will not have a cache entry also. So if you have a page hit, we can use the address translation to access the memory and at the same time update the TLB, then update the cache and send the data to the CPU. If you have a page fault, then we have to access the disk, fetch the missing page, and if we have an empty frame in the memory, update it, update the page table, update the TLB, update the cache, and send the data to the CPU. Otherwise, if there is no empty frame in the memory, we need to find a page to replace. Based on the replacement policy, find the page to replace. If that is dirty, you need to write it back. Then you can overwrite that page in the memory, update the page table, update the TLB, update the cache, send the data to the CPU, right? So those are the two key different ways of incorporating the TLB into the big picture of memory access. It depends on whether the cache is virtually indexed or physically indexed. Right, so that is it for the memory hierarchy section. Next thing we have to talk about is multiprocessors, which we will do in the next lecture, probably next week. So if you have any questions, we can you can ask them and get them clarified here.